Welcome to Professor Explains. Somewhere in Antarctica, in a quiet laboratory kept colder than most winters you have ever known, a scientist is holding a small cylinder of ice. It does not look like much. It is cloudy in places, clear in others, and if you saw it sitting on a table, you might mistake it for an ordinary block of frozen water, the kind you would drop into a glass on a warm afternoon. But this particular piece of ice is 800,000 years old. It is older than our species, it is older than the first cave painting, older than the first word ever spoken, older than the idea of fire being kept rather than feared. And in a moment this scientist is going to do something that sounds almost like an act of gentle magic. Though it is nothing of the sort, it is simply careful, patient science. They are going to crush it. The ice is placed inside a sealed chamber, and the air is pumped out until there is nothing left inside but vacuum, an emptiness as complete as the space between stars. Then slowly, the chamber begins to close and the ancient ice is broken apart under that perfect silence. And in that instant, something is released, a faint hiss, a breath. Tiny pockets of gas sealed inside the ice for 800,000 years finally let go. And here is the part that I want you to hold on to as you settle in tonight, the part that took me a long time to truly believe even after I understood it. That breath is real. It is not a guess. It is not a model on a screen. It is not a clever calculation dressed up to look like certainty. It is the actual air, the actual atmosphere of a vanished world, the same air that drifted over glaciers and tundra and the slow migrations of animals that no longer exist. When that ice cracks open, the gas that escapes is air that a woolly mammoth could have breathed, air that an early human wrapped in fur at the edge of an ice age could have pulled into their lungs on a cold and ordinary morning. We are not imagining what the past was like. We are holding a piece of it in our hands, and we are letting it speak. Stay with me because I want to change the way you picture this ice, and once it changes, I think it will never quite go back. Most of us, when we think about how scientists know what the climate was like long ago, imagine something complicated and a little abstract. We picture them studying clues, reading hints, piecing together a story from fragments the way a detective reconstructs an evening from a few scattered objects. And for a great deal of the deep past, that is exactly what happens. Scientists read proxies, indirect signals, traces left behind by something that is long gone. They look at the shapes of fossilized shells and the chemistry of old ocean mud and the rings of ancient trees, and from all of that they infer, carefully and brilliantly, what the world might have been like. Inference. Educated reading between the lines. And that is real knowledge, hard-won and trustworthy. But it is reading between the lines. The ice is different. The ice does not ask us to read between the lines because the lines themselves are physically present. When that bubble of ancient air comes hissing out of the crushed ice, we are not inferring the composition of the old atmosphere. We are measuring it directly. We are taking the actual gas, the literal molecules that floated through the sky before the first city was ever built, and we are counting what is inside. This is the quiet, astonishing truth at the center of everything we are going to explore together tonight, and I want it to settle into you slowly, the way the snow itself settles, one soft layer at a time. The ice sheet of Antarctica is not a frozen wasteland. It is not an empty white nothing at the bottom of the world. It is a diary. It is the most honest diary the planet has ever kept, and it does not summarize, it does not paraphrase the past or round it off into a tidy lesson. It preserves the past, page by paper-thin page, 2 miles deep, holding the actual air and the actual dust and the actual ash exactly where they fell. We are not reading a description of an old world, we are reading the world itself. So before we go down into it, before we begin our slow descent through those 2 miles and those 800,000 years, let me ask you something. The way I always do, just so I know who is here with me in the dark tonight. Wherever you are listening from, whatever quiet corner of the world is holding you right now, I would love to know. Leave a small note in the comments and tell me where you are. There is something I find deeply comforting about that, the thought of all these scattered lights, all these different rooms in different countries, all settling down to drift off together inside the same slow story. And if you are new here, if you have only just found this calm little place, you are very welcome to stay. A gentle tap on the subscribe button keeps these slow journeys coming to you, night after night, whenever you need, somewhere unhurried to fall asleep. There is no rush. There never is here. Let your shoulders drop. Let the day go. The ice has waited 800,000 years to tell you this. It can certainly wait for you to get comfortable. Now, let us talk about that number, because I said it almost in passing and it deserves far more than that. 800,000 years. It is the kind of number that slides right past you when you hear it, too large to feel, the way a word repeated too many times stops sounding like a word at all. So let me give it a shape you can actually hold. The ice core that holds those 800,000 years comes from a place in the heart of East Antarctica called Dome Sea, and it was drilled by a great collaboration of European nations under a project with a fittingly grand name, the European Project for Ice Coring in Antarctica, EPICA for short. And it is an epic in the oldest sense of the word, a long journey into the deep past. The scientists worked from a research base called Concordia Station, one of the coldest and most remote inhabited places anywhere on the surface of this Earth, a small cluster of buildings sitting on a vast white plateau where the air is thin and the silence is enormous, and the cold is the kind that the human body was never meant to know. And from that lonely station, over years of patient work, they sent a drill down into the ice. Down and down, until it reached a depth of 3,270 meters. 3,270 meters, that is more than 2 miles, straight down through solid ice. And here is where the diary metaphor begins to come alive, because that depth is not just a measure of distance. It is a measure of time. The deeper you go, the older the ice becomes, and the journey downward through those 2 miles is a journey backward through 800,000 years. Every meter you descend carries you across centuries. Every kilometer is multiple ice ages. The very top of the core, the ice nearest the surface, is recent, the snow of our own grandparents' winters. And the very bottom, the deepest ice the EPICA team carefully analyzed, corresponds to roughly 800,000 years before the present day. The whole record was pieced together and published in stages between the years 2004 and 2008, and when it was finished, the world had in its hands the longest continuous diary of the planet's climate ever recovered from the ice. A single column of frozen time, 2 miles tall, with the most ancient page at the bottom and the most recent page at the top. I want you to imagine that you could somehow turn that column on its side and walk along it the way you might walk the length of a very long hallway. You start at the top in our own time and you begin to walk backward. With each few steps, years fall away beneath your feet. Soon you have walked past everyone you have ever known, then past everyone they ever knew. You keep walking. The Roman Empire rises and falls in the space of a single footstep. You walk further, and the Great Pyramids have not yet been imagined. Further still, and the last of the ice ages is gripping the northern world, and you have barely begun. You walk and you walk through that long, cold hallway, and the ice ages come and go beneath you like the slow swing of an enormous pendulum, one after another, and only when you reach the very far end of that impossibly long corridor, 800,000 years from where you started, do you finally arrive at the oldest page the EPICA ice can offer. That is the scale of what we are descending into tonight. Not a story, a library. A library written in frozen water. And here is a detail that makes the whole thing even stranger and more wonderful, a detail that I find myself returning to whenever I cannot quite believe such a record could exist at all. At Dome C, where this ice was drilled, it almost never snows. Or rather, it snows so little that you would hardly call it weather at all. Only a few centimeters of snow accumulate there in an entire year. A few centimeters. In some places in the world, a single storm in a single afternoon can drop more snow than Dome C receives across 12 whole months. It is one of the driest places on the planet, a frozen desert where the air holds almost no moisture, and the snow that does fall is fine and sparse and slow. And at first, that might seem like a problem. Surely you would want lots of snow, you might think, lots of fresh layers piling up to record the years. But it is precisely the opposite, and understanding why is one of the keys to the whole diary. Because the snow falls so slowly at Dome C, each year of the record is incredibly thin. A single year might be compressed into a sliver of ice you could barely see, thinner than a page, thinner sometimes than a fingernail. And that is exactly what allows the record to run so deep into time. If a great deal of snow fell every year, each year would take up a thick slab of ice, and within a few thousand years the drill would have to pass through an enormous thickness of ice to cover even a modest span of time. The record would be detailed, yes, but short. You would run out of ice sheet long before you ran out of years to record. But at a slow, dry, patient place like Dome C, where each year is paper thin, you can stack 800,000 of those thin years into just a few kilometers of ice. The slowness is what gives you the depth. The very emptiness of the sky above Concordia Station is what allows the diary to reach so far back. The years are whisper thin, but there are so very many of them, pressed gently together by the slow weight of all that came after. It is a kind of trade, really. A quiet bargain written into the physics of the cold. Some places, like parts of Greenland, get far more snow each year, and there the diary is wonderfully detailed, with thick, clear pages you can read in fine resolution, where you can pick out individual seasons and even individual years with great precision. But because each year is so thick, those records cannot reach back nearly as far. They are like a diary written in large, generous handwriting, beautiful and easy to read, but filling up quickly. And other places, like Dome C, are the opposite. There the handwriting is impossibly small and cramped, each year a faint, thin line, harder to read in fine detail, but going on and on and on, page after page after page, deeper into time than any other diary on Earth. Tonight we are reading the long one. The slow, thin, patient, deep one. The one that remembers 800,000 years. Now I want to pause on something that troubled the very first people who tried to read these ice diaries, because it is a sensible worry, and you may already be feeling it yourself, somewhere at the edge of your drifting thoughts. If the ice is 2 miles deep and all of that ice is sitting on top of older ice, then surely it is being squeezed and pressed and pushed around down there. Surely it does not just sit politely in neat horizontal layers waiting patiently to be read in perfect order. And that worry is exactly right. Ice, given enough time and enough weight upon it, does not behave like a solid block at all. It flows. Slowly, almost imperceptibly, over thousands and thousands of years, ice creeps and spreads outward under its own enormous weight, the way a thick pool of honey will very slowly flatten and spread if you leave it long enough on a tilted plate. And if the ice is flowing, then the layers within it can be stretched and thinned and dragged sideways, and in the very deepest and oldest ice they can even be folded over on themselves like the pages of a book that has been left out in the rain and warped. And a folded, jumbled diary is no good to anyone. If the pages are shuffled, you cannot trust the order of the story. So how on earth do the scientists find ice they can actually trust to lie in proper order? This is where one of the most elegant decisions in all of this work comes in, and it explains why the drilling site was chosen so very carefully, why they went to that particular lonely dome in the heart of the continent rather than somewhere easier to reach. The answer is that they drill at a dome. A dome in this sense is the high point of an ice sheet, a great gentle summit of ice, and it sits over what is called an ice divide. Picture, if you will, the very crown of a person's head, the spot from which the hair flows down and outward in every direction. The ice does something similar. At a dome, the ice is at its highest, and from that high point, it flows outward and away on all sides, downhill in every direction, the way water would run off the top of a smooth hill. But right there, at the very peak, at the exact summit, where the ice begins to part and flow away in opposite directions, there is a place where the ice barely flows sideways at all. It mostly just sinks gently and straight down under the weight of the new snow falling endlessly above it. And that is the secret. At the dome, at the ice divide, the layers sink almost straight down without being dragged sideways. The pages of the diary stack themselves neatly, one beneath the other, in their proper order, the oldest at the bottom and the youngest at the top, the way layers ought to lie if you want to trust them. The flow that would shuffle and fold the record everywhere else is, at this one special high point, reduced to almost nothing. This is why the scientists traveled so far and endured so much cold to reach Dome C. Not because it was convenient, for it was anything but. They went there precisely because the ice beneath that dome had kept its pages in order, sinking slowly and faithfully down through 800,000 years without scrambling the story. The remoteness, the brutal cold, the impossible distance from anything warm or comfortable, all of it was the price of finding a place where the diary had not been smudged. And so they built their station on that frozen plateau, and they set their drill against the ice, and they began the long, slow work of bringing the pages up, one at a time. I find something deeply moving in that, and I hope you do too here in the quiet. The idea that somewhere out there, in one of the most hostile places the world has to offer, where the cold itself is a kind of danger and the nearest help is impossibly far away, a small group of people chose to live in tents and huts for the sole purpose of reading what the ice remembers. They were not looking for gold or oil or anything you could hold in your hand and sell. They were looking for memory, for the planet's own record of itself. They went to the ends of the earth, quite literally, to crouch over a frozen column and ask it, gently, what it had seen. And the ice answered. It always answers if you are patient enough to listen, and if you go to the one quiet place where it has kept its pages straight. So now we know where we are going, and we know why this particular ice can be trusted to tell its story in order. We are at Dome C, in the heart of East Antarctica, where the snow falls only a few centimeters a year, and each year is pressed into a sliver thinner than a page, and where the ice sinks slowly and faithfully down beneath the dome without folding its memories into chaos. We have a column of frozen time more than 2 miles deep, holding 800,000 years, with the most recent winter at the top and a world from before our species at the very bottom. And we have already met the most astonishing thing about it, the thing I want you to carry down into sleep with you tonight. This diary does not describe the past, it keeps it. The bubbles of air are not clues about the old atmosphere. They are the old atmosphere, sealed and saved and waiting. The dust is real dust that fell from a real ancient sky. The ash is real ash, from real volcanoes that erupted before any human eye was there to see the fire. We are not going to read a story about what happened. We are going to read what happened in the very material it left behind. And so I make you a quiet promise, the same promise the ice makes to anyone willing to descend into it slowly. Tonight we are going to go down through those 2 miles, page by paper-thin page. We are going to learn how a single drop of frozen water can remember the exact temperature of the day it fell from the sky. We are going to learn how the air gets locked away and sealed, and the strange and lovely fact that the trapped air is always a little younger than the ice that holds it, like a letter sealed inside an envelope that was made just slightly earlier. We are going to learn how the years can be counted one by one like the rings of a tree, except these are the rings of the sky rather than the rings of a trunk, written in dust and chemistry and the faint chemical signature of winters and summers long gone. We are going to descend through ice ages and warm ages, swinging back and forth in a slow and ancient rhythm. And eventually, far down at the bottom, we are going to come face to face with the strangest entry in the entire diary, the one the ice itself seems almost not to understand, the page that has no precedent anywhere in all 800,000 years of its long and faithful memory. But all of that is for the slow hours ahead, and there is no need to hurry toward any of it. For now, it is enough simply to stand at the top of the column, here in the quiet, with the snow falling so softly above Concordia Station that you would scarcely feel it on your skin. It is enough to know that beneath your feet, if you were standing there, 2 miles of memory waits patiently in the dark, each thin page sunk gently beneath the last, holding the breath of a vanished world. Imagine that softness, imagine the snow drifting down a few faint centimeters across an entire year, so slowly that a single year is thinner than a whisper, and yet there are 800,000 of them stacked one upon another in perfect quiet order. Imagine the weight of all that time pressing down so gently that nothing is crushed, nothing is lost, only preserved, only kept, only remembered. The cold up there is enormous, but you do not need to feel it. You are warm, and the day is over, and there is nothing left for you to carry now. Let yourself begin to sink the way the snow sinks at Dome Sea, slowly and without effort, settling into the layers below. We have a long descent ahead of us, 800,000 years of it, and I will be with you the whole way down, speaking softly, turning the pages one at a time. There is no part of this you need to stay awake for. If you drift off in the next few minutes, the ice will keep its story safe exactly as it has for all this time, and you can return to it another night and find every page still in its place. That is the gift of a diary that does not describe, but preserves. It is always there. It is always waiting. It never changes the order of its pages or forgets a single line. So breathe slowly now, the way that ancient air breathed out of the crushed ice in that cold and silent laboratory, and let the first layers begin to settle over you, soft and thin and quiet, as we prepare to go down into the deep and patient memory of 2 miles of ice. And here is the first thing to understand about that laboratory, the thing that changes everything once you let it sink in. When the researcher takes that fragment of 800,000-year-old ice and crushes it inside a sealed vacuum, what escapes is not a clue, it is not a hint, it is not a clever guess pieced together from indirect signs. It is the actual atmosphere of a vanished world, the literal air, the same gas that once moved across glacial plains and filled the lungs of creatures long gone to dust. The little bubbles trapped inside the ice are not a proxy for the ancient sky. They are the ancient sky, caught and held and carried forward across hundreds of thousands of years, waiting patiently in the dark until a careful hand opened them again, This is the quiet revolution hiding inside the whole story, and it is worth lingering on as you settle deeper. Most of us assume that to know the distant past, we must reconstruct it, must build a model and reason our way backward through layers of inference, always one step removed from the thing itself. And for so much of deep time that is true, but not here. Not with the ice. Here we do not infer the ancient air. We measure it. We hold it. The ice is not a story written about the past. It is the past kept whole. A diary, yes, but a diary that does not describe its days in words that might be mistaken or embellished. It saves the days themselves, pressed flat and sealed and perfectly preserved, one paper-thin page at a time. Before we go further down into those pages, let me ask you something gently, with no need to answer tonight if you are already drifting. Wherever you are listening from, in whatever quiet corner of this turning world, I would like to know. Some night, if you feel moved to, tell me the place where you let yourself sink into sleep. And if you are new here and you find that this slow descent suits you, you might choose to subscribe. So the next story finds its way to you on the next quiet night. That is all. Let it go now. Sink back into the snow. Now the scale of it. This is the part that asks your tired mind to stretch just a little, slowly, before letting go again. Picture a single column of ice drilled straight down from the surface at Dome Sea, where the European project for ice coring in Antarctica reached its great depth at Concordia Station. That column descends more than 3,000 meters, more than 2 miles, straight down into the white. And every meter of it, every single meter, is not just frozen water. It is time stacked and compressed and held in order. 2 miles of ice contains roughly 800,000 years of the planet's memory. 800,000 winters and summers, 800,000 quiet falls of snow. And how can so much time fit into so little space? Because the snow that falls at Dome Sea falls so very slowly, only a few centimeters each year. Think of that. A whole year of weather, a whole turning of the seasons, the entire breathing of the atmosphere across 12 long months, and all of it leaves behind a layer thinner than your finger. A few faint centimeters, and then the next year settles softly on top, and the next, pressing the year below it gently into the dark. Each year paper thin, and yet the column runs so impossibly deep because there are so very many of them, patient layer upon patient layer, never hurrying, never crowding, simply accumulating in the cold and the quiet for longer than our species has existed. This is the trade the ice makes with us. Low accumulation means each single year is whisper thin, almost too thin to read on its own, but it also means the record runs astonishingly deep, far back into time. Other places, like the ice sheets of Greenland, gather far more snow each year, and there each year is thicker and easier to read in fine detail, but the record there does not reach nearly so far back. At Dome Sea, in exchange for thinness, we are given depth. In exchange for a few centimeters a year, we are given 800,000 years. It is a slow bargain and a beautiful one. But there is a problem hidden in all that depth, and it is the kind of problem that a careful mind worries over, the kind that scientists thought about long before they ever began to drill. If you simply stabbed a drill into any random patch of the great ice sheet, you might not find the years lying flat and in order at all. Because ice, given enough time and enough weight, does not merely sit still, it flows. Slowly, imperceptibly, over thousands and thousands of years, the vast ice sheet creeps and spreads under its own enormous mass, and as it moves, it stretches and tilts and folds the layers within it. And where the layers are stretched and folded, the diary's pages slide out of order, smeared and thinned and tangled, until you can no longer be certain which year sits above which. So the scientists do something clever, something patient, and exact. They do not drill just anywhere. They choose their place with great care, and they choose a dome. A dome is the high, broad crown of the ice sheet, the place that sits over an ice divide, the still point from which the ice flows outward in all directions but barely moves itself. It is the quietest place on the whole sheet. There, at the very top, the ice has the least reason to slide sideways, and so the layers stay stacked the way they fell, vertical and undisturbed, one clean page beneath the next, in the order they were written. That is why Dome C, why Concordia, why these remote and frozen heights, and not some easier place closer to the coast. They are drilling where time stands most nearly still, so that the pages stay in order all the way down. And so we come to the descent itself, which is where we will spend the rest of this long night together. We are going to go down through that column slowly, the way the snow first went down, page by paper-thin page. We will not rush. There is no rushing a diary 800,000 years long, and there is no reason for you to rush towards sleep either. We will sink layer by layer into the cold, reading what each one kept, the air it held, the dust it carried, the temperature it remembered in the very water of itself. Some pages we will read closely, many we will simply pass through softly on our way deeper. You do not need to hold on to any of it. The ice has already done the holding for us for longer than you can imagine, and it will go on holding it long after this night is over. So let the surface fall away above you now. Let the first thin layers close over your head, soft and silent, and begin to sink with me into the patient dark, where the years lie waiting in their perfect order, each one a paper-thin page, each one a held breath of a vanished sky, all of them keeping faith with the past as we go slowly, slowly down. The first thing a scientist learns to read in the ice is not the air. It is the water itself. This is, when you sit with it, a remarkable thing. The ice around every one of those sealed bubbles is not merely a container. It is not inert glass, not a neutral envelope. The water that forms each layer of the column arrived as snow, and before it arrived as snow it was vapor, and before it was vapor it was liquid, somewhere out on the surface of an ocean, lifted into the sky by the warmth of the sun, carried for days or weeks on the high, cold winds, rising and cooling as it moved inland toward the pole, until the temperature dropped just enough that it fell. And in all of that journey, in every single step of the lifting and the carrying and the falling, the water was quietly, faithfully recording the temperature at which it traveled. It was doing this not in any symbol, not in any language we invented, but in the most fundamental way matter can keep a record, in the arrangement of its own atoms. Water, as you may remember from some distant classroom, is built from hydrogen and oxygen. But hydrogen and oxygen each come in more than one flavor. Ordinary hydrogen is light, but there is a heavier version called deuterium, which carries an extra neutron in its nucleus. Ordinary oxygen is also light, but there is a heavier version of oxygen as well, oxygen 18, which carries 2 extra neutrons. These heavier versions are real, natural constituents of ordinary water. Every raindrop, every snowflake, every glass of water you have ever drunk contained a tiny fraction of both. They are not rare or strange, they are simply heavy. And the heaviness is exactly the point. When water evaporates from the ocean and begins its long journey toward Antarctica, the lighter molecules are more eager to leave. They lift more easily. The heavier ones, or the water molecules carrying deuterium or oxygen 18, are slightly more reluctant to become vapor, slightly more inclined to condense back into droplets and fall early. Think of it as a very gentle sorting. A parcel of air rising over the ocean sets out with a certain proportion of heavy and light water. As it cools and some moisture falls as rain, the heavy molecules fall preferentially, a little more readily, than their lighter counterparts. By the time that air parcel has traveled far inland, has risen over mountains, has crossed open ocean, and then the sea ice and arrived at the deep interior of Antarctica in the middle of winter, it has shed most of its original heavy water along the way. The snow that finally falls at Concordia Station is depleted in deuterium and oxygen-18 compared to ocean water, and the colder the air has been along that journey, the more depleted it is. This is the calibration. Climatologists measure the ratio of heavy to light water in snow falling today at various temperatures. They build a relationship, a curve, between the temperature of formation and the isotopic composition of the snow, and then they apply that curve backward into the ancient ice. Every layer of the column, every paper-thin year, contains water whose isotopic ratio was set at the moment the snowflake formed by the temperature of the air it fell through. Colder air during the ice ages left isotopically lighter snow. Warmer air during the interglacials left snow slightly heavier in deuterium and oxygen-18. The difference is small, a fraction of a percentage point, but the instruments used to measure it are extraordinarily sensitive, and the signal is real, consistent, and continuous across the entire column, all the way down. So when a core sample is cut from the ice and the ice is melted in a sealed flask, and the water is fed through a mass spectrometer, what comes out is not an interpretation of the past temperature, but a direct chemical measurement of it, encoded in the water at the moment of its freezing and preserved without alteration for however many thousands or hundreds of thousands of years the ice has been lying there. Scientists use the Greek letter delta to describe this ratio, writing it as delta D for deuterium and delta O18 for oxygen-18, and a graph of those ratios plotted against depth in the core looks, after a moment, startlingly like a graph of temperature through time, which is exactly what it is. This is what it means to say the ice remembers. Not that we have found some clue, some circumstantial evidence, some pattern we have learned to interpret by analogy. The water molecules in a piece of 800,000-year-old Antarctic ice carry within them the actual temperature signature of the air mass that produced them, the same way a wax seal carries the impression of the ring pressed into it before the wax was hard. The seal is the record, the wax is the archive, and it has been waiting, in the cold and the dark, for someone to come and read it. Deuterium and oxygen-18 are therefore the paleothermometers of the ice sheet, and they are the primary reason the column can be read as a temperature history at all. But they have a companion method, a second thermometer, built not into the water but into the borehole left behind when the core is extracted. When the drill withdraws its long, hollow cylinder of ice and leaves a narrow hole behind, that hole does not see the sky. It is sealed at its mouth from the surface conditions, and the rock and ice around it are very slowly over years and decades equilibrating toward a temperature profile set by thousands of years of surface conditions. The ice sheet, in other words, is not a perfectly uniform temperature throughout. At the surface, it reflects the current climate. Deep down, it retains thermal signatures of past climates because ice is not a good conductor of heat. It holds the memory of past warmth or cold slowly, imperfectly, in the way that a thick stone wall holds the memory of summer long into the autumn, not sharply and not perfectly, but genuinely. If you lower a very precise temperature sensor down the borehole and record the temperature at every depth, you get a profile. And that profile is not flat. It undulates gently. It carries a smeared, diffused record of past surface temperatures, a kind of thermal echo of the ice ages written into the substance of the ice sheet itself. Mathematicians and glaciologists can apply inversion techniques to that borehole temperature profile and reconstruct, independently, the history of surface temperatures, the same history the isotopes are recording. The two methods do not always agree perfectly because the borehole record is blurred by thermal diffusion over millennia, but they agree closely enough to validate each other, and in the places where they diverge, the discrepancy is itself informative, pointing to complications in the ice flow history or in the accumulation rate. The borehole at Concordia, the borehole at Vostok, these holes drilled over years of patient work and filled afterward with the dense drilling fluid used to keep them from collapsing under their own pressure. They are not merely access tunnels into the ice. They are themselves instruments. The ice around them is itself a thermometer, a slow one that integrates temperature over centuries rather than minutes, but a real one, and its reading can be checked against the isotopes, and the agreement between them is one of the reasons we can be confident in what the column is telling us. Two thermometers then, one chemical and one thermal, both physical, both independent, both reading the same history, and both within the known limits of each method, telling the same story. But temperature, even confirmed twice over, is only one of the things the ice holds. The second is the air. You will perhaps recall from the earliest moments of this descent the image of a scientist pressing a piece of ancient ice into a vacuum chamber and watching the bubbles release their contents. But it is worth slowing down here because the mechanism by which those bubbles come to exist at all inside the ice and the subtlety involved in reading them correctly is one of the most beautifully exact things in the whole enterprise. When snow falls at Concordia Station, it does not land and immediately becomes solid ice. It piles up as a light, fluffy accumulation of grains with open spaces between them, spaces that connect to each other and to the air above, so that the air flows freely through the upper layers of the snowpack, the way air flows through a loosely packed bag of sand. This unconsolidated snow, once it is a year or more old and has been slightly compressed by the weight of new snow falling above it, is given a name. It is called firn. Firn is the transition state between fresh snow and solid ice, and it is not airtight. It breathes. Air moves freely in and out of it, mixing with the atmosphere above. As more and more snow accumulates over the years, the firn at depth is slowly compressed. The grains are pressed together. The open passages between them are squeezed narrower and narrower, and at some point, typically somewhere between 50 and 120 meters below the surface, the passages finally seal off completely. Individual pockets of air, which up until that moment had been in free communication with the atmosphere above, are trapped. They become bubbles, and from that moment on, the air inside those bubbles is the atmosphere of the year in which the firn closed, preserved under the ice above, never again exposed to the sky. This depth at which the passages seal is called the close-off depth or the lock-in depth. It is different at different sites because it depends on the temperature and the rate at which snow accumulates, both of which vary across the ice sheet. At Concordia, where temperatures are extremely cold and accumulation is very slow, the close-off happens at a greater depth than at some other sites, around 80 to 100 meters down. And here is the subtlety, the thing that requires careful attention. The ice at the close-off depth is not the same age as the air it has just sealed. The ice was deposited as snow many hundreds or even thousands of years before the firn at that depth finally closed off. Think about it this way: the snow that fell at Concordia today will not become airtight firn until it has been buried by many more years of snow accumulation. At Concordia, where only a few centimeters of snow fall each year, it takes a very long time for enough snow to pile up to compress the firn at depth into sealed ice. The result is that by the time the air is finally trapped at the lock-in depth, the ice immediately surrounding those bubbles was deposited centuries earlier. The ice is older than the air it contains. Scientists give this difference a name. They call it the delta age, meaning the age difference between the gas and the surrounding ice. At Concordia, this delta age can be several thousand years, At other Antarctic sites with faster accumulation, it may be only a few hundred. Accounting for this difference is one of the crucial steps in using ice cores correctly. If you want to know whether CO2 in the atmosphere rose before temperature did, or after, or simultaneously, the answer depends entirely on getting the delta age right. It has been the subject of painstaking work over many decades because the question of whether greenhouse gases lead or lag temperature in the glacial cycles is not a trivial one. It touches on the mechanisms driving the whole machinery of the ice ages, and the answer, it turns out, is genuinely subtle. CO2 and temperature are so tightly coupled that disentangling cause from effect at certain points in the record requires knowing the delta age to within decades or centuries across a signal spanning hundreds of thousands of years. The air in the bubbles, once correctly age-matched to the climate record from the isotopes, is then analyzed by a mass spectrometer for its concentrations of carbon dioxide and methane and other trace gases. And what comes out is not a model, not a simulation, not an inference. It is a direct measurement of the actual ancient atmosphere. The CO2 concentration of the air that blew across the tundra 400,000 years ago during the interglacial that preceded the last 4 ice ages is not something we have calculated or estimated. It is something we have measured from the gas itself, extracted from the ice that has held it since before our species had a name for fire. This is the distinction that makes ice cores unlike almost any other climate archive. Tree rings tell us about temperature and rainfall, but indirectly through the way they affected the tree's growth. Ocean sediments tell us about sea surface temperatures, but through the chemistry of tiny shells deposited on the seafloor, each one the end product of a biological process that itself depends on many variables. Cave formations, these slow-grown mineral columns inside limestone caverns, record the chemistry of groundwater that passed through the rock above, and from that chemistry we can infer rainfall and temperature, but again, indirectly, through chains of reasoning. All of these are proxies. They are records of something else that happened to be sensitive to climate. They are fingerprints, not the hand itself. The air bubble in the ice is the hand itself. It is the atmosphere, the actual mix of molecules that drifted through the air of a vanished world, trapped, sealed, carried down through the centuries on the slow conveyor of snowfall and compression, and held there in the cold and the dark, waiting. Now comes the third layer of what the ice reads, and it is one that rewards extended attention because it opens a window not into one slow, continuous signal, but into the sharp detail of individual years. In a place like Greenland, where snow accumulates much faster than at Concordia, the annual layers in the ice are thick enough to be distinguished one from the next. And the tools for doing so are several, which is fortunate, because any one of them alone would be less convincing than all of them working in agreement. The first tool is dust. In summer, when the atmosphere is more active and the jet streams shift and winds carry continental material off the great land masses to the south and east of Greenland, more mineral dust arrives in the snowfall. In winter, when the atmosphere is more stable and the source regions are locked under their own ice and snow, less dust arrives. So the dust content of the ice rises and falls on a seasonal rhythm like a pulse, and in the cores from GS2, the Greenland Ice Sheet Project 2, and from NGRIP, the North Greenland Ice Core Project, this pulse can be resolved layer by layer, counted the way you count the rings of a tree, each dark band a summer, each pale band a winter, each pair together 1 year's entry in the diary. The second tool is the chemistry of the snow itself. Different seasons bring different chemical signatures. Sulfate concentrations tend to peak in spring, carried from lower latitudes on the seasonal winds. Sea salt sodium arrives more abundantly during winter storms. Nitrate follows its own pattern. Each of these chemical signals oscillates in and out with the seasons, and each is another clock, another way to assign a year to a layer of ice. The third tool is electrical. When electrical current is passed through the ice, its conductivity varies with the chemistry of the ice. Acid layers, deposited after volcanic eruptions or during certain seasons, conduct electricity differently from neutral layers. An electrical conductivity measurement run continuously along a core produces a profile, a kind of electrical fingerprint of the annual layers, and it can be read with the same logic as the dust or the chemistry. And the fourth tool is the isotopes themselves. The same deuterium and oxygen-18 ratios that tell us about long-term temperature also oscillate on the seasonal cycle because summer precipitation and winter precipitation fall from air masses at different temperatures. The seasonal isotope cycle is smaller than the glacial-interglacial swing, much smaller, but in a high accumulation site like Greenland, where each year's worth of snow is thick enough to analyze at fine resolution, it is detectable. These four tools, dust chemistry, electrical conductivity, and isotopes, run in parallel, and when they agree on the same layer boundary, there is very little room for doubt. The GISP2 and NGRIP cores allow this kind of annual layer counting to reach back tens of thousands of years into the Greenland record, providing a time scale of exceptional precision for events of the last glacial period. It is, in the deepest sense, what the phrase "tree rings of the sky" is meant to capture. The same logic that a forester applies when pressing a fingertip to the rings of a felled oak, reading drought years, wet years, cold years, years of plenty, is being applied here to the atmosphere itself. One winter and summer pair at a time, each pair thinner than a page, stacked in the dark beneath Greenland's surface all the way down to the bedrock. In the Antarctic cores, particularly at Concordia, the annual layers are far too thin to count directly in this way. The accumulation is so low, only a few centimeters of snow per year, that an individual year's worth of ice is compressed to a sliver that cannot be resolved with these chemical and physical tools. Instead, the age model for the Antarctic cores must be built by other means, by matching volcanic events in the core to volcanic events in Greenland, whose layers can be counted and dated by using mathematical models of ice flow and accumulation to project depth into age. By looking at the methane signal, which is globally mixed in the atmosphere and appears nearly simultaneously in Greenland and Antarctic cores, allowing the two records to be synchronized at key events. These are robust methods tested against each other and against independent dating approaches, but they are not as direct as counting layers. They involve some uncertainty, which grows as you go deeper, and the ice grows older, and the accumulation rate is harder to reconstruct. The error bars on the age of the deepest EPICA ice are measured not in years, but in thousands of years, a testament to both the remarkable precision achieved and the honest limits of the method. This is the appropriate moment to mention something that is sometimes left out in shorter accounts of ice core science, and which is worth holding in mind as we continue the descent. The ice does not only record what happened to the atmosphere from above, it also carries, faintly but measurably, the thermal history of the ground from below. The ice sheet at Concordia is not in perfect thermal equilibrium. At the surface, it reflects the current climate, the brutally cold, dry, high-altitude conditions of the East Antarctic plateau. At the base, the ice rests on rock, and the rock carries geothermal heat rising slowly from the interior of the Earth. The temperature at the very base of the ice sheet at Concordia is warmer than the temperature in the middle of the column. Not much warmer, but warmer, because the geothermal heat keeps the bottom from freezing as solid as the interior. And between the surface cold and the basal warmth, the temperature profile of the column bends in a gentle curve that encodes, as I described earlier, the integrated thermal history of the surface conditions over long timescales. When you lower a thermistor on a cable down the borehole left by the drill, recording temperature every few centimeters, you get that curve. And buried in it, like a signature smoothed by time but not erased, are the echoes of the last glacial maximum, 20,000 years ago, when the surface was much colder, when the snowflakes that fell carried lighter isotopes, when the dust was thicker and the CO2 in the bubbles was lower. That cold event reached down into the ice sheet the way cold reaches into a stone floor in winter. It is still there, diffused and blurred by tens of thousands of years of thermal conduction, but there. The ice sheet is, in the most physical and literal sense, still holding the cold of the last ice age in its body. And so the borehole thermometry and the isotope paleothermometry read the same past by different mechanisms, one through the chemistry of the water itself, frozen at the moment of its fall, the other through the thermal state of the ice mass, retaining faint echoes of surface temperatures integrated across millennia. They do not give exactly the same answer, because one is a high-resolution record of individual snowfalls and the other is a low-resolution thermal average that has been blurred by diffusion, but they constrain the same history, and their broad agreement is one of the most satisfying confirmations in the entire science. The ice knows what temperature it was formed in, and it knows what temperature it has been kept at since, and it will tell you both if you ask it in the right language. We are perhaps 80 meters into our descent now in the metaphor of the dive. The fern has closed off above us. The air in the bubbles we are passing through was sealed when these same layers were at the close-off depth, meaning the air is somewhat younger than the ice we are sliding through, the delta age doing its quiet, invisible accounting around us. The isotopes in the water are reading winter. This is old winter, perhaps 3,000 years old, perhaps 5,000. The specific number depending on where exactly we are in the column and what the accumulation history has been. And the ice is reading the temperature at which it fell as precisely as a thermometer left in a snowflake for the entire journey from the ocean to this place. Somewhere above us, if we could look back up through the transparent column, we would see the 20th century, the 19th, the medieval warm period, the cold spell that settled over the northern hemisphere in the centuries around the Little Ice Age, the gradual warming of the early Holocene, as the great ice sheets of the last glacial maximum slowly retreated. All of that is above us now, already passed through, each layer logged in the water and the air and the dust, each page turned. Below us lies everything else. The long undulation of the Holocene, 10,000 years of relative stability that allowed human civilization to take root and grow. Deeper still, the abrupt and dramatic transition at the end of the Younger Dryas, when climate flipped from near glacial cold back to warmth in timescales almost incomprehensibly short. Deeper still, the full sweep of the last glacial maximum, the world of mammoths and ice walls and expanded deserts, the world those sealed air bubbles actually breathed. And deeper still, further back than any human memory, further back than the earliest writing or the oldest city or the first use of metal, back before all of that, the slow, deep oscillations of the ice ages themselves, 8 full glacial, interglacial cycles preserved in the column, their temperatures written in deuterium and oxygen. 18, their atmospheres held in the bubbles, their years counted in dust and chemistry and electrical signal, all of it waiting in the cold and the dark, patient as only the very old can be patient. We have, in this second passage of our descent, learned 3 things about how the diary is written, and they are worth holding loosely the way you hold a thought at the edge of sleep. You do not need to grip them. They will be there. The first is that the water itself is the thermometer. Heavy hydrogen and heavy oxygen sorting themselves out of the clouds over the ocean, riding the cold air inland, falling as snow that is lighter in heavy isotopes when the air is colder, heavier when the air is warm. Every snowflake that ever fell at Concordia arrived already carrying its temperature signature in its own atoms, and it has never let that signature go. The ice is made of thermometers that have been reading the same measurement for hundreds of thousands of years without drifting, without needing new batteries, without anyone to check them. The second is that the air in the bubbles is real. It is not analogous to ancient air, not modeled from ancient conditions, not reconstructed from something else that was sensitive to ancient air. It is the air, sealed between 50 and 100 meters below the surface, younger than the ice that holds it by anywhere from a few centuries to a few thousand years, depending on the site and the accumulation rate, but real, physical, measurable, the actual CO2 and methane molecules that were suspended in the atmosphere of the world during whatever year those bubbles closed. When a researcher extracts that gas and feeds it into a mass spectrometer, she is not doing archaeology. She is doing chemistry. She is measuring what is there. And the third is that the layers can be read in sequence, year by year, in the places where the accumulation is high enough, and by subtler means where it is not, and the resulting timescale, carefully built and cross-checked by multiple independent methods, gives us a diary with page numbers. Not merely a pile of undated entries, but a book, in order from the most recent page at the top to the oldest at the bottom, with enough confidence in the ordering that we can speak of this interglacial or that ice age with a precision measured in centuries or millennia rather than vague geological eons. And the borehole itself, the long, quiet cylinder of cold left behind by the drill, holds in its walls the thermal memory of the same history told by the chemistry, a second copy in a different medium, written slowly, read slowly, checked against the first. These are the instruments the ice carries inside itself. Not instruments we bring to the ice, but instruments the ice has been running continuously by the laws of physics since before there was anyone to read them. We have only recently learned the language, and the ice has been writing in it all along. Let that settle now as we continue to descend. The column goes on below us, very much deeper than we have yet gone, holding much older entries. The mechanisms of reading, the isotopes, the bubbles, the layers, the borehole temperature are all established now, all in place, all quietly working as we sink further into the cold. What remains is the reading itself. What remains is what the diary actually says, page by page, century by century, ice age by ice age, all the way down to the oldest ice anyone has yet recovered, and beyond that to the ice that is still being chased. So let the column close quietly around you now. Let the faint, seasonal pulse of dust and chemistry move past without demanding attention. Let the isotopes do their patient recording in the water all around, and the bubbles hold their ancient breath in the dark, and the borehole carry its slow thermal echo upward toward a surface that feels very far away. We are inside the diary now. The pages go on below us for a very long way, and there is no need to hurry. The first human beings to read these deepest pages did not arrive all at once, and they did not arrive easily. The story of how we got to the ice at all is itself a story of cold and distance, and the particular stubbornness of people who had decided that what lay beneath the Antarctic plateau was worth suffering for. Vostok Station sits on the East Antarctic plateau at an elevation of about 3,488 meters above sea level, which is high enough that the air is thin and the sky at noon has a particular hard blue to it that people who have been there describe as unlike any other sky anywhere. The station was established by the Soviet Union, and for decades it was a place of punishing isolation, reachable only by difficult overland traverses across some of the most featureless terrain on Earth. The annual mean temperature at the surface of Vostok is approximately -55 degrees Celsius. The record low temperature ever recorded at Vostok was -89.2 degrees Celsius in 1983, the coldest naturally occurring temperature ever measured at a station on the Earth's surface at the time of its recording. The people who wintered there did so in a tradition of polar science that had more in common with early Antarctic exploration than with the comfortable research stations of later decades. They stayed because the ice beneath them was worth staying for. Drilling at Vostok proceeded in stages across several decades, and it was a collaboration that crossed the Cold War. Soviet scientists, French scientists, American scientists, working at various points together and in complex logistical partnership in one of the most remote places humans have ever inhabited for scientific purposes. The drill went down through meter after meter of compressed centuries. Firn in the upper layers, true ice below, and then deeper ice, older ice, ice that had been compressed and slightly deformed by the weight of everything above it, but still carrying its record intact enough to read. The core came up in segments, each segment a cylinder roughly 10 centimeters across and about a meter long, cold and faintly translucent, handled with the care you would give to something irreplaceable, because it was. When the Vostok drilling reached 3,623 meters, the team stopped. Not because the ice ran out, not because the drill failed. They stopped because the instruments told them that beneath the ice, at that depth and a little beyond, there was something unexpected, something that had been known about theoretically for some time, but whose full extent had become clearer as the drilling progressed. There was a lake down there, a real lake, liquid water, sealed from the surface of the Earth, not for centuries, but for what was estimated to be millions of years, an entire ecosystem, if any life existed in it, that had been completely isolated from the outside world longer than our species has existed, subglacial Lake Vostok. It is one of the largest subglacial lakes on Earth, roughly the area of Lake Ontario, sitting in a basin beneath more than 4 kilometers of ice, kept liquid by geothermal heat from below and by the insulating pressure of the ice above, which lowers the freezing point of water slightly. The decision to stop drilling just above the lake was not a casual one. It was a recognition that whatever was down there, whatever chemistry, whatever possible biology, was irreplaceable in a way that even the oldest ice above it was not. You can drill more ice cores, you cannot unseal a lake that has been sealed for millions of years. The caution was genuine and it was right, and the decision has shaped polar drilling ethics ever since. The 3,623 meters of Vostok ice that were recovered before that halt, however, those were extraordinary. The record they carried stretched back approximately 420,000 years. 4 ice ages and their intervening warm periods were written in those cores. The paper that presented the full record, Petit and colleagues, published in the journal Nature in 1999, has been cited thousands of times and is among the most influential paleoclimate papers of the modern era. What it showed for the first time in a single, continuous, beautifully resolved record was the rhythm of the ice ages themselves, laid out like a piece of music that had been playing beneath the planet's feet for longer than our species had walked on them. Temperature and greenhouse gases going up together and down together, cycling through 4 great oscillations, the pattern so clear and so consistent that when you look at the graph, the first reaction is not analysis, but something closer to recognition. Yes, of course, the planet breathes, and here is the proof of it: 4 full breaths drawn slowly over 420,000 years. That record was already astonishing. And then came Dome C. Concordia Station sits at a place on the East Antarctic plateau called Dome C, which is itself sometimes referred to in the technical literature as Dome Charlie, named in the Convention of Antarctic Geodesy. Like Vostok, it is remote, among the most remote, permanently inhabited places on Earth. Unlike Vostok, Concordia Station is a joint French-Italian facility built specifically for the kind of deep ice science that requires long stays and patient drilling. It sits at an elevation of about 3,233 meters, and the annual mean temperature is roughly -54 degrees Celsius. In the austral winter, the sun does not rise for several months. The people who winter at Concordia do so in complete isolation from the rest of the world in a way that very few humans experience, and they have done so in the service of a question about what the ice remembers. The project that drilled at Dome C was the European Project for Ice Coring in Antarctica, EPICA, a collaboration of 10 European nations that recognized that the Vostok record, magnificent as it was, left open a question that could only be answered by going deeper, which at a low accumulation dome site like Dome C meant going further back in time. The EPICA core at Dome C reached 3,270 meters. That is slightly shallower than Vostok in absolute depth, but because of the extremely low accumulation rate at Dome C, only a few centimeters of snow per year, pressed year after year into millimeters of ice, those 3,270 meters contain twice as much time. The ice at the bottom of the EPICA Dome C core is approximately 800,000 years old. The results were published progressively between 2004 and 2008, and what they revealed extended the Vostok record backward through 4 additional ice ages, giving a total of 8+ complete glacial interglacial cycles, all of them written in the chemistry and isotopes and gas bubbles of a column of ice no wider than a human arm. 8 ice ages, the number is worth holding for a moment, not the concept of ice ages in the abstract, not the theoretical understanding that the Earth has been through them, and the actual physical record, the direct measurement, the ice itself saying, here is the first one, 800,000 years ago, and here is how cold it got, and here is how much carbon dioxide was in the air, and here is how much dust was blowing across the continents, and here is when the methane dropped, and here is when the ice sheets grew, and here is when they melted 8 times over. In sequence, readable, right there in the ice. And the rhythm of those cycles, that is the next thing the ice says, once you have established that it is speaking at all, because the 8 ice ages in the EPICA record are not random, they are not chaotic fluctuations in some unpredictable system. They come and go with a cadence that has a shape to it, a period, a timing that corresponds to something outside the planet itself. It corresponds to the slow changes in Earth's orbit and orientation as it moves around the Sun over geological time. These are the Milankovitch cycles, named for the Serbian mathematician Milutin Milankovic, who, working in the early 20th century, calculated that variations in Earth's orbital path would change the distribution of solar energy reaching different latitudes at different times of year, and that these changes would be sufficient to trigger ice ages. There are 3 main orbital parameters that change on their own distinct timescales. Eccentricity describes the shape of Earth's orbit, how elliptical or how nearly circular it is. This varies on a timescale of roughly 100,000 years. Obliquity describes the tilt of Earth's rotational axis relative to the plane of its orbit, a parameter that affects how extreme the seasons are, with more tilt meaning more severe summers and winters, less tilt meaning more moderate ones. Obliquity cycles on a time scale of roughly 41,000 years, and precession describes the slow wobble of Earth's axis, like the wobble of a spinning top that is beginning to slow, which changes which hemisphere points toward the Sun at what time of year. Precession cycles on a timescale of roughly 23,000 years. Each of these operates simultaneously, and their combination produces a complex but ultimately calculable rhythm of variation in the solar energy reaching Earth's surface at different latitudes and seasons. The ice record does not need to be told about Milankovitch cycles, it has simply recorded them. When you look at the 800,000-year EPICA record, the dominant rhythm of the glacial interglacial cycles runs close to 100,000 years, matching the eccentricity cycle. Within that, subtler variations at the 41,000-year and 23,000-year timescales are also visible in the finer structure of the isotope and gas records. The ice did not know what it was recording. It simply froze the snow and trapped the air and preserved the dust year by year for 800,000 years, and the orbital cycles of the solar system are written into it as clearly as lines on a page. Now, the carbon dioxide and methane records. And these are what the bubbles tell us, and the bubbles are the most direct part of the diary, the part where there is least room for ambiguity. The air was there. The air was trapped. The air is still there, perfectly sealed, and when we crush the ice and release it, we measure exactly how much carbon dioxide and methane it contained at the moment of its entrapment. Over the 800,000 years of the EPICA record, carbon dioxide oscillated between roughly 180 parts per million during glacial cold periods and roughly 280 to 300 parts per million during interglacial warm periods. That range, 180 at the bottom of an ice age, 280 to 300 at the warmth of an interglacial like the one we inhabit, is the natural range of atmospheric carbon dioxide across 8 complete glacial cycles. It is a range the planet has returned to again and again, the system's natural breathing, the same rhythm as the ice and the temperature, going up and down in step. 180 ppm, cold, dry, dusty, ice-covered world. 280 ppm, warm, wet, forested world. The ice knows both. Methane tells a similar story. Over those same 800,000 years, methane in the ancient atmosphere oscillated between roughly 350 to 400 parts per billion during glacial periods and roughly 650 to 700 parts per billion during interglacials. The sources of methane in a warm world are different from those in a cold one. Warmer, wetter climates produce more methane from wetlands and tropical forests, while cold, dry, glacial conditions suppress those sources. So the methane record tracks the same rhythm as temperature and carbon dioxide, rising when the world warms, falling when it cools, and doing so across all 8 cycles with a consistency that looks, once you see it, almost like a rule of nature rather than a coincidence. The relationship between greenhouse gases and temperature in the ice record is tight and real, and has been one of the most studied features of the paleoclimate literature since the Vostok data were published. But it is also worth being honest about what the record shows and what it does not show, because the ice is not a simple story, and the planet's climate system is not a simple machine. Temperature and carbon dioxide track each other with striking fidelity over the long sweep of the record, rising and falling together across the glacial cycles. That much is clear and unambiguous. But within the fine structure of individual transitions, the relationship is more complex. At some points in the record, particularly at the beginnings of deglaciations, the transitions out of ice ages into warm periods, the temperature signal in the ice begins to rise slightly before the carbon dioxide rises measurably in the bubbles. This is not a flaw in the data. It is a feature of the climate system, and it reflects the fact that carbon dioxide is not the only driver of these transitions, and that the carbon cycle itself has inertia. The way it works is something like this. The Milankovitch cycles change the distribution of solar energy, which triggers the initial warming at certain latitudes and seasons. That warming begins to melt ice and thaw permafrost and change ocean circulation, and the oceans, which hold enormous reservoirs of dissolved carbon dioxide, begin to release some of that carbon into the atmosphere as they warm, because warm water holds less dissolved gas than cold water, in the same way that a warm soda goes flat faster than a cold one. As the carbon dioxide rises in the atmosphere, it amplifies the warming through the greenhouse effect, which causes more melting, which releases more carbon, and the whole system accelerates. The feedback loop. So carbon dioxide is both a response to initial warming and a powerful amplifier of that warming. It does both things at once, lagging slightly behind the first temperature pulse and then driving the temperature higher than it would have gone on Milankovitch, forcing alone. The ice records all of this, all the nuance, all the complexity. It does not simplify the story, it just tells it honestly, and it falls to us to read it carefully enough to hear what it is actually saying rather than what we expect it to say. Alongside the temperature and gas records, the ice carries another kind of archive, one that speaks not of gradual cycles, but of individual events, violent events, catastrophes on the geological timescale, events that altered whole landscapes and poured enough material into the atmosphere to leave a mark in the ice at the other end of the Earth. These are the volcanic layers. When a large volcano erupts, it throws enormous quantities of sulfur dioxide into the stratosphere, where it reacts with water vapor to form sulfate aerosols, tiny droplets of sulfuric acid that spread around the globe on stratospheric wind patterns, eventually settling back to Earth and getting buried in the ice. In an ice core, a volcanic eruption appears as a spike in sulfate concentration, a sharp chemical signal against the quieter background of ordinary accumulated snow. These spikes can be detected by measuring the electrical conductivity of the ice. Sulfate makes ice conduct electricity more readily than clean ice does, and in some cases they appear as visible features, slightly different in texture or transparency from the layers above and below. In other cases, the eruption delivers not just sulfate chemistry but actual physical fragments of volcanic glass, tephra, tiny shards of solidified magma, each one with a chemical fingerprint as distinctive as a signature, identifying not just the fact of an eruption but the specific volcano that produced it. A tephra layer in an ice core is one of the most powerful tools available to the people who read these archives, because it is an absolute time marker in a way that most other signals are not. If a tephra layer can be matched by its geochemistry to a known eruption with a known date, say a large eruption that was recorded by historical societies or that can be dated by other geological methods, then that layer becomes a fixed point, a nail in the calendar that pins the surrounding ice to a specific year. Above and below that fixed point, the counting of annual layers or the modeling of accumulation rates can be anchored to something real and externally verified rather than extrapolated from the accumulation record alone. The tephra layers are where the ice's memory connects to history, the moments where we can say with confidence, this layer is from this year, and everything above it and below it is datable relative to that anchor. Some of the volcanic signals in Greenland ice cores have been matched to historical eruptions whose dates are known from written records. Icelandic volcanoes, Hekla, Laki, Katla, have erupted repeatedly over the centuries in events documented by Norse settlers and later by European observers, and their signatures appear in Greenland ice at the expected depths, the chemical fingerprints confirming what the historical records say. The volcanic chemistry in the ice agrees with the history, and the history agrees with the ice, and between them they validate each other across methods, across archives, across kinds of evidence entirely. This is how science builds confidence, not from one line of evidence but from the convergence of many, each independent, each pointing to the same answer. But the ice does not only record the planet's own internal events, it records the outputs of human civilization as well, and some of those records are sobering in a particular way. The ice cores from Greenland, drilled not for deep time but for high-resolution recent history records, the GIS-2 and GRIP cores reaching back over 100,000 years with exceptional detail for the more recent millennia, show the chemical fingerprint of ancient industry written into the layers thousands of years before the Industrial Revolution. Lead pollution, specifically. Lead is a metal that has been smelted by human beings since antiquity, and the smelting process releases lead into the atmosphere, where it travels on wind patterns and eventually settles into the snow. In the Greenland ice, there is a measurable rise in atmospheric lead deposition that corresponds to the period of Roman industrialization, the expansion of Roman mining and metallurgy, the widespread use of lead in plumbing, and in the production of sweeteners and preservatives that the Romans derived from lead compounds. Roman lead is in the Greenland ice. The peak and the subsequent decline correspond to the trajectory of the Roman economy, rising as the empire expanded its industrial capacity, falling as the empire contracted in late antiquity, rising again as medieval industry developed, then spiking again in the Industrial Revolution, and then producing a particular and pointed signal in the 20th century. That 20th century signal is leaded gasoline. From the 1920s onward, tetraethyl lead was added to gasoline as an anti-knock compound, and the lead released by burning hundreds of millions of gallons of leaded fuel every year dispersed globally and settled into ice on the other side of the world. The Greenland ice cores show a sharp spike in lead deposition that begins in the early 20th century and climbs steeply through the post-war decades, then drops, measurably, clearly, written in the ice after the phase-out of leaded gasoline that began in earnest in the 1970s and continued through the following decades. The ice recorded the introduction of a pollutant, the peak of its use, and its removal from the environment. The ice recorded, in other words, a human decision and its consequences etched into the layers the way all other events are etched, by the chemistry of what fell from the sky in that year, preserved in the cold, waiting to be read. There is one more archive the ice carries that belongs in a different category from the volcanic chemistry and the atmospheric gases and the isotopic temperature signals. It is an archive of something beyond the planet itself, an archive of the Sun and of the strength of Earth's own magnetic field, written in a trace element called beryllium-10. Beryllium-10 is produced in the upper atmosphere by a process called cosmogenic nuclide production. High-energy particles from space, cosmic rays, strike atoms of nitrogen and oxygen in the upper atmosphere and produce, among other things, beryllium-10, which then settles through the atmosphere and accumulates in the ice. The rate at which beryllium-10 is produced depends on how many cosmic rays reach the upper atmosphere, and that depends on two shielding factors. The first is the Sun. When the Sun is more active, when sunspot activity is high and the solar wind is strong, the heliosphere, the bubble of solar wind that surrounds the solar system, deflects more cosmic rays before they reach Earth. More active Sun means fewer cosmic rays. Reaching the atmosphere means less beryllium-10 produced means lower concentrations in the ice. The second shielding factor is Earth's own magnetic field. A stronger magnetic field deflects more cosmic rays and produces less beryllium-10. A weaker field lets more through. So the beryllium-10 record in the ice is a measure of the combined effect of solar activity and geomagnetic field strength over the timescales the ice covers. A proxy for things happening not just on Earth, but in the space around it. Spikes in beryllium-10 in the ice record can indicate periods of reduced solar activity, solar minima, the quieter phases of the Sun's roughly 11-year activity cycle, and the longer period variations that modulate it over centuries and millennia. They can also indicate periods when Earth's magnetic field was weaker than usual, allowing more cosmic radiation through. By comparing beryllium-10 records in ice cores from different parts of the world, Greenland and Antarctica, scientists can begin to separate the global signal of solar activity from the more regional signal of geomagnetic variation, because solar changes affect both poles simultaneously, while geomagnetic changes are more complex in their geographic expression. And the beryllium-10 records from multiple cores can be used to synchronize cores from different drilling sites, providing a global reference signal that allows the independent records to be aligned on the same timescale. The ice, through beryllium-10, carries a record not just of the climate, but of the space environment that surrounded the Earth during the time the ice was forming. A record of the Sun, of cosmic rays, of the magnetic field that shields the planet, all written into the accumulation of a trace element in the snow that fell on Antarctica and Greenland year after year, century after century, before we knew it was being written. All of this, the volcanic layers, the lead from Roman forges, the lead from 20th century highways, the beryllium-10 from cosmic rays deflected or emitted by the Sun, and the geomagnetic field is happening at the same time as the isotopic temperature record and the greenhouse gas record, all in the same ice, all in the same stack of compressed seasons. The ice is not a single archive, but a simultaneous archive of many different things, a library where many books are shelved in the same physical space, their pages interlocked, each one adding something the others cannot provide. You read temperature from the water, you read gas concentrations from the bubbles, you read volcanic chronology from the sulfate and the tephra, you read solar and geomagnetic history from the beryllium-10, you read human industrial history from the trace metals. And all of them are there together in the same centimeters of ice, speaking simultaneously about the same moments in time, each in its own language, each available to a reader who knows how to listen. The dust is in there too, and the dust is worth staying with for a moment, because the dust tells a story that the gas record and the isotope record do not tell in quite the same way. The story the dust tells is one of wind and aridity and the texture of glacial worlds. Not just how cold they were, which the isotopes record, and not just how much carbon was in the air, which the bubbles record, but how they felt on the surface. What the land was like. What was blowing across it. During glacial periods, during the cold phases of the 100,000-year cycles, the dust in Antarctic ice is dramatically higher than during warm interglacial periods, not slightly higher, often 10 times higher or more. The ice of a full glacial maximum is visibly dustier than interglacial ice, not always to the naked eye in thin slices, but clearly in the analytical measurements, the concentrations of insoluble mineral particles that were lofted into the atmosphere somewhere on the cold, dry continents and carried to Antarctica on the global circulation of wind. And the reason for that difference tells us something about what glacial worlds were actually like. In a glacial world, not only were the ice sheets expanded and the global temperature lower, but the climate was also profoundly drier. Continental interiors became deserts, where now there are grasslands or forests. Sea levels were lower because so much water was locked in the ice sheets, which meant that the continental shelves, the shallow underwater margins of the continents that today are submerged, were exposed land. And exposed continental shelf without vegetation, without rivers, without the stabilizing effect of moisture, is a source of dust. The wind picked it up. The wind carried it across the cold, clear, dry glacial atmosphere with less resistance than the warmer, moister interglacial atmosphere would provide, and it settled eventually in the Antarctic snow, and it was compressed into the ice, and it stayed there. And now we read it, and we can say something about not just the temperature of those glacial worlds, but their texture. The fact that they were windy and pale and bare in ways the world is not now. The landscape stripped down to mineral soil and blown about, the dust traveling thousands of miles to land on the ice at the bottom of the world and tell us what the continents looked like when the ice was at its height. The dust layers are thickest during the depths of the glacial maxima and thinnest during the interglacials, with gradual transitions in between that track, the slow coming and going of the ice ages themselves. And within that broad pattern, individual dust events sometimes appear. Sharp spikes in a single season's ice corresponding to a particularly violent dust storm or a drought that stripped an especially large area of soil in a short time. The ice records these too, the individual catastrophes within the longer rhythms, a single terrible season preserved at a particular depth alongside all the other signals of that year. The chemistry, the isotopes, the gases, the volcanic sulfate, if an eruption happened then, the beryllium-10 tracking the sun. A year in the ice is a dense and complicated thing, full of information from many directions at once, all of it compressed into a thickness that might be no more than a few millimeters at the depth of a glacial maximum at Dome Sea, where the slow accumulation rate means that each year is very thin indeed. And this is one of the most important facts about the Dome Sea record and about the EPICA core in general. The very quality that makes it so valuable for deep time, the low accumulation rate, the fact that it snows so little at Dome Sea that 800,000 years fit into 3,270 meters is also the quality that makes it less useful for reading recent, high-resolution history. At Dome Sea, each year near the bottom of the core may be compressed into a few millimeters. Individual years cannot be distinguished at those depths. The record is a deep time average, not a year-by-year transcript. It is a diary written in a very compressed script where each line covers decades or centuries rather than days or weeks. Magnificent for reading the sweep of the glacial cycles, less suited for reading the fine structure of rapid transitions. And that is where the Greenland cores, with their higher accumulation rates and their annual layer resolution, complement the Antarctic record. Each site doing what it is best at, the two together spanning a wider range of questions than either alone. The EPICA Dome Sea record, then 800,000 years, 8 glacial interglacial cycles, the Milankovitch rhythms written into the ice, greenhouse gases oscillating between their natural bounds, dust at glacial maxima, volcanic spikes, beryllium-10 from cosmic rays, lead from Roman and 20th century industry, all of it stacked in a column of ice at one of the coldest and most remote places on Earth, recovered meter by meter through years of patient drilling, published in papers that have been read and cited and built upon by scientists on every continent. It is the longest continuous climate record from a single source that we have. It reaches back to a time before modern humans existed, before the species from which we descended had yet separated from our closest relatives, before the cave paintings and the stone tools that mark the oldest traces of human symbolic thought. 800,000 years is a number that does not yield easily to imagination, but the ice holds it with complete indifference to how difficult we find it to comprehend, and what the ice says about those 800,000 years is something we can, with care and time and the right instruments, actually read. And what it says, across all 8 cycles, across every glacial and every interglacial, across the full span of the record, is that the natural range of the planet's carbon dioxide over those 800,000 years runs between roughly 180 parts per million and roughly 280 to 300 parts per million. Those are the low and high bounds of the natural system, the range within which the Earth's climate has breathed in and out over 8 complete cycles of ice and warmth. 180 at the coldest, 280 to 300 at the warmest. And then there is now, and now is not inside those bounds. But that page is not yet written in this particular part of the reading. The ice still has more to say before we arrive at the present, and the present will be more meaningful when we understand more fully what precedes it, what the ice found at its deepest and oldest levels, and what it could not preserve, and what lies just beyond the reach of the longest record we have yet recovered in ice, older than anything yet brought to the surface. The drilling continues, the questions are waiting in the ice, and there is still very far to go before we reach the bottom. There is something the ice did not always do slowly. That is perhaps the most unsettling entry in the whole diary, not the grand sweep of 8 ice ages, not the lockstep rise and fall of carbon dioxide across hundreds of millennia, but the passages where the ice is writing in a different register entirely, where the seasonal layers are not slowly shifting but lurching, where what the isotopes record is not a gradual warming or a measured cooling, but something that looks, when you read it carefully, like a door slamming open or a door slamming shut. Climate science is often associated with slow change, with processes measured in centuries and millennia, with the patient accumulation of ice and the patient melting of it, with Milankovitch cycles that take tens of thousands of years to complete their geometry. and most of the ice record is indeed slow. Most of it breathes on those grand timescales, the 100,000-year pulse, the 41,000-year rhythm, the 23,000-year wobble. But buried inside the Greenland cores, inside the ice recovered at GISP-2 and at GRIP, the two deep drilling projects that reached bedrock on the central Greenland ice sheet. There are entries in the diary that are written in a completely different hand. They are called Dansgaard Oeschger events, named for Willy Dansgaard, the Danish glaciologist who pioneered the use of stable isotopes in ice cores, and Hans Oeschger, the Swiss physicist who contributed foundational work to understanding the records those isotopes produce. Dansgaard and Oeschger identified in the Greenland cores a pattern of abrupt climate changes during the last glacial period, a pattern that repeats itself on the order of a few thousand years, dozens of times across the Ice Age. And when you look at what those events actually record, the sensation is something close to vertigo. During a Dansgaard-Oeschger event, the temperature over Greenland, as recorded in the deuterium and oxygen-18 ratios of the ice, rose by somewhere between 8 and 16 degrees Celsius, not over 10,000 years, not over a millennium, over decades, sometimes over a single human lifetime. The ice shows warmings of 8, 10, 12, even 16 degrees occurring fast enough that a person born into a glacial cold snap could, if they lived long enough, grow old in a climate that had transformed almost beyond recognition. This happened not once, not twice, dozens of times during the last glacial period. The Greenland cores document more than 20 such events, each one a sudden lurch into warmth followed, more slowly, by a gradual cooling back toward glacial conditions until the next abrupt warming came. Think about what that means in terms of the pace of change. The world you knew as a child, the winters, the snowpack, the rivers, the vegetation, could be substantially different from the world your grandchildren knew. Not because of any human action, because the climate system under the conditions of the last ice age was capable of reorganizing itself on a timescale measured in human generations. The ice shows this. It shows it not as inference, not as a model output, but as a direct record in the layers. The isotopic composition of the snow that fell shifts abruptly and unmistakably within the space of a few centimeters of ice, representing a few decades of time. The mechanisms behind Dansgaard-Oeschger events are still debated among researchers involving the behavior of ocean circulation in the North Atlantic, the movement of sea ice, the feedback loops between ice sheets and the atmosphere. The ice records that these things happened with great clarity and precision. The full explanation of why they happened on these timescales remains an open and active area of science. But the fact of them is written in the ice as plainly as anything the diary contains. Repeated, verified across multiple cores, and deeply important to understanding what the climate system is actually capable of. And then there is one particular Dansgaard-Oeschger event, or rather one particular aftermath of a period of climate disruption, that has a name of its own and that appears in the Greenland ice with a vividness and an abruptness that still astonishes researchers who have spent careers reading these records. It is called the Younger Dryas, and it represents something almost as startling as the warming events themselves. A sudden reversal, a snapping back toward glacial cold at a moment when the world had already begun to warm, followed by a final, decisive, extraordinarily rapid lurch into the warmth of the Holocene, the geological epoch in which all of recorded human history has taken place. The Younger Dryas lasted from approximately 12,900 years ago to approximately 11,700 years ago. During those 1,200 years, the world, and particularly the Northern Hemisphere, experienced a return to near glacial conditions after an earlier warming had already begun following the peak of the last ice age. The reasons for this cooling episode involve Again, the behavior of ocean circulation, the fresh water discharged into the North Atlantic from melting ice sheets, the reorganization of heat transport around the globe. But what the Greenland ice records at the transition out of the Younger Dryas, the moment when the cold finally broke and the Holocene began, is one of the most dramatic single passages in the entire diary. The warming at the end of the Younger Dryas, approximately 11,700 years ago, was not gradual. Some proxies in the ice suggest the final transition occurred within a few years. Some analyses suggest it may have taken as little as a decade. Within the annual layers of the Greenland cores, researchers can see the chemistry of the ice shifting, the dust content dropping, the isotopic ratios swinging toward warmer values, the electrical conductivity changing. Over a span of ice representing perhaps 10 to 20 years of accumulated snow, the world that came before the Younger Dryas, a world still in the grip of Ice Age conditions, still cold and dry and dusty, gave way within what may have been a single human generation to something that began to look climatically like the world we know. The forests spread, the ice retreated, the megafauna of the Ice Age, the mammoths, the woolly rhinoceroses, the cave lions, entered their final centuries. This is the context in which modern human civilization emerged, not in a climate that had been stable for millions of years, but in a world that had only recently come out of one of the most abrupt climate transitions in the ice record. The Holocene, our epoch, the last 11,700 years, has itself been remarkably stable compared to the chaos of the glacial period, and that stability may be part of what allowed agriculture, settled societies, and written history to emerge and persist. But the ice reminds us that stability of that kind is not the default condition of the climate system. It is something the record has to produce on purpose, so to speak, and it has not always done so. All of this, the Dansgaard-Oeschger events, the Younger Dryas, the transition into the Holocene, is written in the Greenland cores with a precision and a temporal resolution that the Antarctic cores, for all their extraordinary depth of time, cannot match. This is the trade-off built into the geography of the archives. Greenland accumulates snow faster than East Antarctica, sometimes 10 or 20 times faster, which means each year of ice in Greenland is thicker, the seasonal layers are more distinct, and you can count them and read them at higher resolution. The cost is that the record does not go nearly as deep in time. The Greenland ice cannot take you back 800,000 years, but it can take you with extraordinary clarity through the most turbulent chapters of the climate story closest to the one we are living now. And it is that question of depth, of how far back the ice can go and what happens to the record as it ages, that brings us to one of the most difficult and fascinating problems in the entire field of ice core science. The ice is not a passive archive. It does not simply sit there accumulating year after year in perfect undisturbed layers waiting to be read from the top all the way down to the bottom. It moves. Ice is a solid, but it is a solid that deforms over time under its own weight and the weight of everything above it, and the deformation of ice over geological timescales means that the older ice, the ice near the base of a sheet that has been accumulating for hundreds of thousands of years, does not look the way the upper ice looks. It has been squeezed and stretched, and in some cases folded. The annual layers, which near the surface of a dome sea core might be a few centimeters thick, thin with depth until they become almost impossibly thin. Near the bedrock at Dome C, layers representing thousands of years of accumulation are compressed into centimeters, and in some cases where the ice has been deformed enough, the layers do not even remain in order. They fold back on themselves like the pages of a book that has been bent and twisted, so that what appears to be a continuous sequence in a vertical core may actually contain repeated sections, or sections that are out of chronological order. This is not a failure of the science, it is a physical reality of what happens to ice under pressure over vast spans of time, and the researchers who work with these cores understand it very well. But it means that reading the oldest and deepest ice requires not just extracting the core, but working out, through multiple independent methods, whether the sequence you are looking at is intact, whether the chronology is reliable, and whether the signal you are reading is a genuine record of a single point in time or a mixture of material from different periods. The techniques for doing this are sophisticated and painstaking, cross-referencing the isotopic record with other chemical signals, looking for the volcanic ash layers and the sulfate spikes that provide absolute time anchors, using the measured thickness of the ice layers to build flow models that predict how much compression should have occurred at each depth. This challenge, reading folded and thinned and potentially disturbed ice, is at the heart of the most ambitious ice core project now underway, the project that represents the next frontier of the diary and that aims to extend the ice record further back in time than any core yet recovered. The project is called Beyond EPICA Oldest Ice, abbreviated as BOIC, and it is being pursued at a site in East Antarctica called Little Dome C, not far from the Concordia Station, where the original EPICA Dome C core was drilled. The reasoning behind this particular site is careful and deliberate. The goal is to find ice old enough to extend the continuous climate record from the 800,000 years of the EPICA core towards something approaching 1.2 million years, possibly further. The project's aims reach toward 1.5 million years, though that figure is best understood as the horizon being chased rather than a result already achieved. What makes Little Dome C a promising location is a combination of factors, including the thickness of the ice sheet there, and modeling work suggesting that the ice at depth, while compressed, may still retain readable stratigraphy, intact enough layers, even if thinned to extraordinary slimness, to allow scientists to decode the climate signal they contain. In 2025, the Beyond EPICA team announced that they had reached bedrock at approximately 800 meters of depth. The ice recovered from the lower sections of that core is being analyzed with great care. Preliminary indications suggest that the continuous record may extend toward 1.2 million years, with the possibility of older basal ice that may be discontinuous or disturbed, but still analyzable. The work of dating and interpreting that ice is ongoing, and the full results will take time to publish and verify, but the direction is clear and the target is specific, and it points toward a question that has been sitting at the edge of the ice record for decades, waiting for the technology and the patience and the extraordinary human effort required to reach it. That question concerns the Mid-Pleistocene Transition. It is one of the genuinely unresolved puzzles in the science of Earth's climate history, and understanding it requires first understanding the rhythm that came before the rhythm we know. The 8 glacial cycles that the EPICA core records, the roughly 100,000-year pulse that has governed Earth's ice ages for the last 800,000 years, was not always the dominant rhythm. Before approximately 1.2 to 0.7 million years ago, the Earth's climate was cycling in and out of ice ages on a different schedule, approximately every 41,000 years, following the cycle of Earth's axial tilt, the obliquity component of the Milankovitch orbital forcings. The 100,000-year cycle that we think of as the characteristic rhythm of the Pleistocene ice ages was not yet dominant. The world was still cold and warm, still glaciated and interglacial, but on a shorter and more regular cycle, one that tracked a different aspect of the Earth's changing orbital geometry. And then, somewhere in the window between 1.2 and 0.7 million years ago, that rhythm changed. The 41,000-year cycle gave way gradually and incompletely to the 100,000-year cycle. The ice ages began to last longer and to reach lower temperatures. The transitions became more dramatic. Something in the climate system shifted. Something in the relationship between orbital forcing and the response of the ice sheets, possibly involving the growth of larger ice sheets, possibly involving changes in ocean circulation, or in the long-term drawdown of atmospheric carbon dioxide by geological processes, and the planet began dancing to a different beat. This transition is called the Mid-Pleistocene Transition, and it is not yet fully explained. Climate scientists have hypotheses. The ice cores that exist, covering the last 800,000 years, show the tail end of the transition and everything that came after it, but they do not reach back far enough to capture the transition itself, to see the climate record from the 41,000-year world and follow it through the change into the 100,000-year world. That is exactly what the Beyond EPICA ice, if it proves readable and continuous, would provide. Ice old enough to show not just the post-transition world, but the transition itself. What the carbon dioxide was doing, what the temperatures were doing, whether the greenhouse gas record shows a role for CO2 in driving the shift, would be an extraordinary page in the diary, a page we have not yet been able to open. It may be there, in the ice at Little Dome Sea, waiting in layers so thin that a researcher holding a section of core in gloved hands would find it nearly impossible to believe it contains anything legible at all. But the instruments are sensitive enough, the methods are refined enough, and the question is important enough that teams of scientists are spending seasons at one of the most remote and inhospitable places on the surface of the Earth to find out. Which brings us to something worth pausing on, a misconception that surfaces sometimes in the way this research is described, and that the ice itself quietly but firmly corrects. There is a way of talking about old ice, and specifically about the ancient air trapped inside it, that sometimes reaches toward the image of dinosaurs, as if the ice could carry us back to the Mesozoic, as if crushing an ice core in a vacuum might release something a Tyrannosaurus or a Brachiosaurus once breathed. It is a vivid image, and it is entirely wrong. The oldest ice that has ever been recovered, the oldest ice the Beyond EPICA project is hunting, reaches back toward 1.2 million years at the outermost limit of current ambition. The non-avian dinosaurs disappeared approximately 66 million years ago. There is no ice, and there could be no ice that bridges that distance. The polar ice sheets themselves in their current form are geologically young. What the ancient air in those ice cores carries is not dinosaur breath. It is something closer to us in time, though still fantastically remote. The atmosphere breathed by the woolly mammoths, by the cave bears, by the early members of our own genus making their way across Ice Age landscapes, by the Neanderthals who existed in parallel with us through much of the time span the Greenland cores record. That is the right scale of the astonishment. The air released from an 800,000-year-old bubble of EPICA ice was breathed by creatures that would not have recognized a city or an alphabet or a field of wheat, but it is air from a world that is, in the deep time frame of geology, almost recent. The ice gives us the Pleistocene, the dinosaurs are elsewhere, in rock. And yet, even within its proper scale, what the ice gives us is more than enough to hold every wondering thought you might want to bring to it, because the record it carries, 800,000 years of temperature, greenhouse gas, dust, ash, solar activity, industrial pollution, ends in something that no previous page of the diary contains. The natural range of atmospheric carbon dioxide over the entire 800,000-year ice record runs, as the EPICA measurements show, from roughly 180 parts per million during the coldest depths of glacial periods to roughly 280 to 300 parts per million during the warmest peaks of interglacials, 8 ice ages, 8 interglacials, 8 complete cycles of the planet breathing in and out, advancing its ice and retreating it, dropping its CO2 and raising it. And in every single one of those cycles, the carbon dioxide stayed inside that range. It reached its interglacial high, 280, sometimes approaching 300, just as it was at the start of the Holocene, the warm period in which we live. And then it turned around. It has always turned around in every cycle the ice records because orbital forcing eventually shifted the geometry again because the feedbacks that amplify warmth eventually ran into the physical limits of what the climate system could sustain at those CO2 concentrations. Modern atmospheric carbon dioxide, measured not from ice cores but from instruments monitoring the atmosphere directly at stations like Mauna Loa in Hawaii, where continuous measurements have been kept since 1958, surpassed 420 parts per million in the 2020s, not 310, not 300, not the interglacial maximum that the ice has recorded at the top of every warm period for 800,000 years, 420 parts per million, and rising above any value that appears anywhere in the entire span of the ice record, above any value the ice has ever preserved from the natural world that preceded us. Methane tells the same story in its own register. The natural range of atmospheric methane in the ice record runs from roughly 350 to 400 parts per billion during glacial minima to roughly 650 to 700 parts per billion during interglacial warmth. Modern methane concentrations in the atmosphere exceed 1,900 parts per billion. That number has no analogue anywhere in the 800,000-year record. It exists outside the entire range of values the ice has ever written down, in a space the diary has never visited before. This is not an inference. It is not a model projection. It is what the ice, the same ice that measured the ancient atmosphere by trapping it physically inside its crystal structure, the same archive that records the CO2 of 8 ice ages and 8 interglacials with direct measurement rather than proxy estimation. This is what that ice says when you set its 800,000-year record beside the atmosphere of the present. The present is off the page, not slightly above the interglacial maximum, not at the high end of the natural range, off the page. The ice has no entry to compare it to because the ice has never seen anything like it before, and that is the entry we are writing now in this century into the planet's most honest diary. The ice will record it. Future ice forming layer by thin layer at Dome C and at Little Dome C and at the other sites where snow is still accumulating in Antarctica will trap today's atmosphere in its bubbles and preserve it as all the ice before it has preserved what it found. If someone in some future age with the technology and the curiosity and the access were to drill down through the ice that is forming right now, they would find the CO2 layer of our time the same way we find the CO2 layer of 800,000 years ago, direct, physical, unchangeable, a bubble of our air sealed in ice, waiting. That future core would show what we showed to the ice. And what we showed to the ice has no precedent in the record of the 800,000 years that came before. There is a way to hold this that is not only unsettling. The ice record is, among other things, a record of resilience, of a planet that has been through 8 ice ages and 8 interglacials, that has survived volcanic eruptions massive enough to leave visible ash in every core that spans them, that has accommodated the rise and fall of dust storms covering continents, that has watched the solar output fluctuate and the Earth's magnetic field shift and still continued its slow, rhythmic breathing. The planet is not fragile in the way a single ecosystem is fragile. The diary records extraordinary events, and the planet survived them, continued, and wrote more pages. What the ice does not tell us, what it cannot tell us, being only a record of what was, not a prediction of what will be, is what the page we are currently writing will mean for the specific conditions that allow human civilization, as we know it and as it has developed in the extraordinary stability of the Holocene, to persist and thrive. That is a different question, and it is not a question the ice answers. The ice answers only what happened. What happened across 800,000 years in temperatures and greenhouse gases and dust and ice and air is preserved in those meters of compressed snow with a completeness and a precision that still moves the researchers who work with it, who hold a core section in gloved hands under the lights of a cold laboratory in Antarctica or in the freezers where extracted cores are archived, and who know that what they are holding is not a representation of the past, but a piece of it. That is what the diary is, not a book written about the past, but the past itself, made dense and cold and portable. And this is what makes the ice so unlike almost anything else in the scientific world. Most of what we know about deep time comes from inference, from the chemistry of ancient rocks, from the fossil record, from the isotopic ratios of minerals that formed under conditions we can only model and approximate. The ice is different. The ice is direct. When the scientists at the EPICA project analyzed the CO2 content of a bubble of ice from 800,000 years ago, they were not calculating what the CO2 probably was. They were measuring the CO2 that was there. The ancient air was in their instruments. It had been in the ice. Before the ice, it had been in the atmosphere of a world before our species existed, breathed by creatures we know only from their bones. And now, for a moment, it was in a laboratory in Antarctica or in Europe, measured, recorded, added to the record. Another page turned, another entry decoded. The drilling continues at Little Dome C. The cores come up, meter by careful meter, handled with the kind of attention you would give to something irreplaceable, which is exactly what they are. Each meter of ice recovered from the deepest sections, ice that may be more than 1 million years old, is logged and photographed and sampled with small, precise cuts that take what is needed for analysis and preserve the rest. The ice that is not immediately analyzed is archived in frozen storage, kept at temperatures cold enough to prevent any alteration of the air bubbles sealed inside it, held for future researchers with future questions and future instruments capable of answers we cannot yet frame. The question of what lies at and beyond the Mid-Pleistocene Transition, what the CO2 and temperature record looks like in the transition from the 41,000-year world to the 100,000-year world, whether the greenhouse gas record holds a key to understanding why the rhythm changed, may be answered in the years ahead as the BEOIC cores are dated and analyzed, and the results move through the careful process of scientific review and publication. Or it may turn out that the deepest ice at Little Dome C is too disturbed, too folded, too compressed to yield a clean, continuous record across that crucial interval. And the question will wait for another site, another approach, another generation of researchers willing to spend their seasons in one of the coldest and most remote places on Earth for the chance to read a few more pages of what the planet has written down. Either way, the ice will be there. The ice does not hurry. It does not lose patience with the slowness of human inquiry or with the centuries it takes to build the technology to drill it and read it, or with the decades it takes to analyze and understand what has been recovered. It accumulates its centimeters of snow each year, at Dome C and at Little Dome C, and at all the other cold, high, quiet places where the world is still writing its diary in the only medium that preserves the atmosphere itself. And it waits. That is what 2 miles of ice remembers, not a model, not an approximation. The actual temperature of the air, encoded in the weight of water molecules that fell as snow on a continent no human had yet walked, and the actual composition of that air, sealed in bubbles that have held it unchanged through 800,000 years of everything the planet has done since. The actual dust of droughts that lasted millennia. The actual ash of volcanoes that no human witnessed. The actual sulfate of eruptions that cooled summers in places where no summer had yet been named. The actual lead of Roman smelters and the actual lead of 20th century automobiles, both written into the same archive in layers separated by 2,000 years of ice. The actual record of a climate system that warmed 16 degrees in a human lifetime dozens of times, and then settled into the stability we mistook for the natural state of things, and then received, in this last thin layer at the top, an atmosphere it has never seen before. When you think of it that way, it's diary written not in ink, but in the physical substance of the world itself, The 2 miles of ice become something almost sacred in their patience and their completeness. Most of what the universe does leaves no trace. Most of what the atmosphere was in any given year of the last million years is gone, dispersed, impossible to recover. But here, at these cold and remote and improbable places on the southern continent, something extraordinary happened. The snow kept falling, and it kept falling gently enough that each year's layer came to rest on the last, and the pressure of what came above slowly sealed the air between the crystals, and the cold held it, and it did not melt, and it waited for us to come and find it and learn to read it. We are still learning, we are still drilling. The questions that remain are what caused the Mid-Pleistocene Transition, what exactly drove the Dansgaard-Oeschger events, what the record beyond 1.2 million years will show when we can finally reach it and read it, are genuine questions with genuine uncertainty, and the ice may take years or decades to yield its answers, if it yields them at all. Science at this frontier moves slowly, carefully, with tremendous respect for the difficulty of what is being attempted and the irreplaceability of what is being analyzed. But what we have already read is astonishing enough to hold a lifetime of wonder. 8 ice ages, 8 interglacials, 100,000 years of breathing in, 100,000 years of breathing out, temperature and carbon and dust and ash, and the sun's activity and the Earth's magnetic field, all written down in layers thin as paper, stacked 2 miles deep in the silence of the East Antarctic ice sheet, waiting in the dark and the cold for someone to come and ask what the planet remembers. And the planet, patient and precise and completely indifferent to whether anyone asks, has been keeping the record all along. Let that settle, if you would, for a moment. Somewhere in Antarctica, right now, in the deep cold of a polar night that lasts months, or in the thin, sharp light of a summer that barely warms the surface, snow is falling on the ice sheet at Dome C. Each flake that lands is another few molecules of today's atmosphere caught and held, the beginning of what will eventually, under the weight of centuries more of snowfall, become tomorrow's ice, and next century's, and the century after that. The record is still being written. We are part of the record now. And somewhere far below that fresh surface snow, under kilometers of ice that grew before we existed, the ancient air of a world before us waits in its bubbles, exactly as it was, unchanged. If you are listening to this from somewhere far from Antarctica, from a bedroom somewhere in the northern hemisphere, or the southern, from a city or a village or somewhere in between, then you are breathing air that is part of the same atmosphere that those bubbles contain, the same continuous column of gases that has wrapped this planet for billions of years, transforming and shifting and being recorded in this extraordinary thin window of time we can reach in the ice. You are part of the record. The air you breathe tonight will not be sealed in ice the way the ancient air was sealed, unless by some chance it finds its way to a polar region still capable of producing ice thick enough and cold enough and enduring enough to hold it. But it is the same air. It is all the same air, the same planet, the same continuous story that the ice has been patiently writing down for 800,000 years and is writing still. Where are you listening from tonight? Wherever you are in the world, I would genuinely like to know. The ice does not record names or addresses, but it records the atmosphere we all share, and there is something in that, in the fact that the air above your particular piece of the planet is part of the same global archive that the Antarctic cores have been reading. That is quietly extraordinary. If you feel moved to share where you are listening from, the comments are there, and I read them. And if this kind of slow descent into the deep past is something you find yourself returning to, there are more stories here of the same careful and unhurried kind waiting for whenever you want them. For now, though, the ice has said what it has to say for this night. The cores are back in their frozen archive. The drill is still. The snow is still falling at Dome C and at Little Dome C and on the vast white surface of the ice sheet that holds 800,000 years of planetary memory in its depths, patient and cold and extraordinary. The questions are waiting in the ice, and you have done enough for one night. Put down whatever remains of the day. Let the cold and the quiet of those ancient layers be something restful rather than unsettling, because the ice, for all it records about change and disruption, and the startling abruptness of a climate that can shift in a lifetime, has also held steady through everything. 2 miles deep, 800,000 years, still there. Lectures over, even the professor sleeps. Good night.